Okay, we're at section 1.3, dimensional analysis. Let's bring up the PowerPoint and go to the next slide. And dimensions. In physics, dimensions denote the physical nature of a quantity. Example, the distance between 2 points can be measured in feet, meters, or furlongs, all different units for expressing the dimension of length. The symbol to specify dimensions of length, mass, and time are L, M, and T. We use brackets to denote dimensions of a physical quantity. As examples, the symbol for speed, V, velocity, is length over time. And the dimension of area is L squared because it's a length by a length. The table lists dimensions and units of area for volume, speed, and acceleration. So the dimensions are L squared, volume are L cubed. Why? Because you have base, the base height, width, or length, height, width, however you want to call it. But you have three lengths that you're measuring. Speed is the length over time, meters per second, miles per hour. All of those are length over time. And acceleration is length over time squared. Now, don't let the time squared bother you. You might, let's say you increase your speed by 5 miles per hour every second, so it would be 5 miles per hour per second. So those are a time divided by time, it ends up time squared. So don't let that intimidate you. Okay, let's next slide. Dimensional analysis can be used because dimensions can be treated as algebraic quantities. Quantities can be added or subtracted only if they have the same dimensions. Terms on both sides of the equation must have the same dimensions. So you use dimensional analysis to determine whether an expression has the correct form. Any relationship can be correct only if the dimensions on both sides of the equation are the same. And it helps you if you're expecting meters per second and you end up with kilograms, you know that something is wrong. Or if you know that you're expecting length over time and you get mass, again, something is wrong. The equation for the position of a car at time t, if the car starts from rest at x equals 0 and moves with a constant acceleration a, is given by the expression x equals 1/2 a of t. The correct expression is given there. The quantity x on the left side has dimension of length. For equation to be dimensionally correct, the quantity on the right must also have dimension of length. So let's perform dimensional analysis by checking and substituting the dimensions for acceleration and time into the equation. So the x has a dimension of length, and of course, the 1/2 is dimensionless. Acceleration is length over time squared, and the t is time, and we square it, it's time squared. So the t squared divided by t squared gives you, they cancel out as the red line indicates, and you get L equals L. So the equation is correct. The dimensions of time cancel, leaving the dimensions of length on the right-hand side and on the left-hand side. Let's see. The more general approach, the more general procedure using dimensional analysis is set up an expression of the form x is proportional to a to the n t to the m. The relationship is correct only if the dimension on both sides are the same. So the dimension on the left side is equal to length. The dimension on the right side must also be length. So whoops, whatever, there you go. Length equals length to the 1, t to the 0. And it ends up being length and length. Because dimensions of an acceleration are L over t squared and dimension of time equals t, the exponents of L and t must be the same on both sides of the equation. From exponents of L, n equals 1. And from the exponents of t, m minus 2 to the n equals 0, which gives m equals 2. Return to the original expression, x is proportional to a to the n, t to the m. We conclude that x is proportional to at squared. And this is one method. I don't use it that much. I use the actual dimensions of mass, meters, and seconds. You'll see how I use it in future examples. But they teach dimensional analysis, so we'll go ahead with it in the book. It can be useful. Let's do a quick quiz. True or false? Dimensional analysis can give you the numerical value of constants of proportionality that may appear in an algebraic expression. Let me read that again. Is this true or false? Dimensional analysis can give you the numerical value of constants of proportionality that may appear in an algebraic expression. Give you a little time to think about it. And the answer is false. It will not give you constants of proportionality. All it does is compare units, and what you want is to end up with the same type of units on either side of the equal sign. Okay, dimensional analysis gives the units of the proportionality constant, but provides no information about its numerical value. To determine its numerical value requires either experimental data or geometrical reasoning. For example, in the generation of the equation x equals 1/2 at squared, because the factor 1/2 is dimensionless, there is no way to determine it using dimensional analysis. Okay, let's go to an example. Now, analysis of an equation. Show that the expression v equals at, where v represents speed, a is acceleration, and t an instant in time, is dimensionally correct. Okay. Identify the dimensions of v. Well, v is equal to length over time. Miles per hour, meters per second. It's a length over time. Identify the dimensions of a, the acceleration, and multiply it by the dimensions of t. Well, acceleration is length over time squared. You multiply that by time, you end up with length over time. Well, look at that. Length over time is the same as a velocity. Therefore, v equals at is dimensionally correct because we have the same dimensions on both sides, L over t. Okay, let's get another example, analysis of a power law. Suppose we were told that the acceleration a of a particle moving with uniform speed v in a circle of radius r is proportional to the same power of r, say r to the n, and some power of v, say v to the n. Determine the value of n and m and write the simplest form of the equation for the acceleration. So you write an expression for a with a dimensionless constant of proportionality k. A equals k, r to the n, v to the m. You substitute the dimension of a, r, and v. So dimensions of a are length over time squared, and you have L to the n for r, and L over t, that's velocity to the m. Equate the exponents of L and t so that the dimension equation is balanced. So solve the two equations for n plus m equals 1 and m equals 2. Let's see, write the acceleration expression Okay, I'm sorry, n equals to -1. We write the acceleration expression. A equals k r to the -1 v squared. K equals v squared over r. We'll learn that that's our centripetal acceleration equation later on. When we start when we study uniform circular motion, we see that k is equal to 1 if a consistent set of units is used. The constant k would not equal 1 if, for example, v were in the form of kilometers per hour and you wanted a in meters per second. This ends section 1.3, the dimensional analysis section. Next, we will study the conversion of units in section 1.4.